Remember when I told you that when I was in high school and I took calculus, I got a 2 on a test? 2 out of 100, not like 2 out of 4, but like 2 out of 100. And it was on this chapter. So I want to help you learn from my mistake. When I was in calculus, there was pressure to just like learn a formula and use it over and over and over again and just perform really complicated calculations to evaluate my integral. But I didn't write the correct integrals because I didn't really understand what's going on. So this process that I've suggested, where we use the different colors to draw in the radius and a green slice, I hope you'll use that. I've been collecting ideas over the last long time to try to help us to understand, so that you know when you write an integral what you're really adding up infinitely many of, so that you can make sure you have the right model, so that when you spend a bunch of time trying to evaluate your integral, at least you're evaluating the correct integral. So I hope you'll hang in there. I hope you will continue trying to use those colors to draw a picture that you understand and use that to lead you to an integral that you understand. I don't want you to have the same experience I did. And so now that we've practiced this a little bit, there's just 2 other things that might be a little more complicated about your picture that we're going to have to understand what to do. But drawing these pictures is going to help you make the connection, so I hope you'll keep doing it. So one of the possibilities, we're talking about solids of revolution. So if you take an area in the plane and you're going to spin it around some line to make a solid that if you sliced it perpendicular to the axis of spinning, you get, well, hopefully we get discs. We'll talk about that if you don't. That's the second complication. So all the examples we did in the last section of notes were revolving around either the x-axis or the y-axis. So you could also be asked to revolve an area around an axis that is not one of the coordinate axes. So we're going to take a look at how our calculations, how our picture change once the axis isn't one of the coordinate axes. So check out this problem. It came from a real live AP test. Oh, I say I've modified it. I wonder how I modified it. So I have a region R, and they gave me a picture this time. You won't always have a picture, but most of the time on the AP test, at least in the free response section, you will. And I've been told that the y equals x, that boundary is that horizontal line is the top boundary, x equals 2 is the vertical boundary on the right-hand side. And I've been asked to find the volume of the solid that I get when I take R and I spin it around the line, the axis of revolution, y equals 6. So I'm going to move me out of the way so that I can start to make my picture. So things I know already. I know I've been asked to, I have R. R is already shaded, so that's nice. I'm going to draw in my axis of revolution. I've been told that's the horizontal line, y equals 6. Now I'm going to sketch in what it would look like if I reflected R around that axis. It doesn't have to be a beautiful picture. You don't necessarily need to mark any points on it, but there's my rough sketch of a reflection of R. Can I write an expression for the volume of the figure that comes from revolving R around the line y equals 6? So what am I going to do next? I'm going to change to green because I'm going to try to draw a slice. I've revolved around the line y equals 6, which is horizontal, and I'm supposed to take my slices perpendicular to that axis. So I'm going to take slices that are vertical. That tells me that the thickness of my slice is going to be a very small change in x. I'm going to draw that in. So remember the rules. This is the first time we've had to go in a different direction. I'm going to start drawing my slice at the axis of revolution. I'm going to draw toward the original boundary. So I'm going to draw toward the edge of my double picture, but I'm going to draw toward the side where I actually know the equation for the boundary. So this region R that's down here, that's where I actually know the equations, right? My reflection up here, I don't want to aim for that. I want to aim for down here. So I'm going to aim for the curve whose graph I know, back up behind the axis of revolution, and back down here. All right, so that's a slice. If I sliced it and looked at it, I'd be looking at a green circle. I'm going to add up the volumes of infinitely many, infinitely thin slices. And we said the thickness of every slice is going to be a very small change in x. So I'm going to write dx. That tells me I'm going to have to write an integral in terms of x. What am I going to put inside my integral? Well, essentially, it's got to be the volume of a cylinder. Just remember that the cylinders are going to be infinitely thin, so the height is the dx. The part that's not going to look like it's infinitely thin is the other part of the volume of a cylinder. That's the pi r squared part. That's the part that comes from the area of the circle before it gets multiplied by the thickness. So in here is supposed to go pi r squared. The dx is like the h. It's the thickness of the slice. So that's great. I could probably already figure out what my x limits are because I'm writing an x integral. I'm going to have to put x limits on it. I can see here that the furthest left x in my picture is 0, and the furthest right x in my picture is 2. Sometimes I'll have to do work to figure that out, but here it was pretty clear. And the only thing holding me back from full credit on this answer is that I have this variable r when I'm supposed to write an integral that only has x's. So that's that last part of the picture that we're going to draw. We're going to draw in the radius. So look at your green slice. Put your blue marker on the axis of revolution and try to draw in a radius of the green slice. So I'm going to put here's the center of the green slice. I'm going to draw, and notice I drew downward because I'm trying to draw toward a function whose equation I know. I could have drawn up, but then I'm gonna bump into some function up there, and nobody told me the equation for it. I could figure it out, but it's more, it would just be more work. So I've drawn toward the thing I know. Okay, so this is where the complication comes in, because look at that blue thing that you drew. We have to write an expression for the length of that blue line segment. Watch what happens. Notice your blue line segment, it's vertical. So if I want to find the length of a vertical line segment, I subtract the y values. Because the two x values on that blue line at the top and the bottom, they're the same because a vertical line has the same x coordinate everywhere. So if I want the distance on that blue segment, I need to subtract top y minus bottom y. Well, look at what the top y is. Your y coordinate at the top of your line segment, it was supposed to be a point on the axis of revolution. Do you know what the y coordinate there is? It's got to be 6. Right? So this is what changes when my axis isn't a coordinate axis. All of a sudden I have another number here that I have to deal with. So notice if I'm going to subtract top minus bottom, that's going to be 6 at the top minus, where does the bottom of my blue line segment hit? Well, it's this function 4 natural log of 3 minus x. 4 natural log 3 minus x. All right, if at this point you're convinced that what I wrote in blue is an expression for the radius of every slice, that's great. Go back and write that integral that we were writing. You're going to use this for r. If you're not convinced, consider trying to draw another slice. I'm going to start my slice at the axis of revolution. I'm going to draw toward the curve I know, all the way back here. There's my slice. Now I'm going to try to draw the radius. Ideally, that's a straight line. What's the top of my radius? The top of my radius is on that red line, and the red line is, I need the y coordinate. The y coordinate is 6. I'm going to check out the bottom of my blue radius. It hits that curve that we were talking about, 4 natural log of 3 minus x. So that's going to be the bottom of my curve, and I'm going to write an expression, top minus bottom, to find the distance of that vertical line segment. So once I've got all that figured out, I'm just going to go back and write my integral. This is going to be integral from 0 to 2, because I've decided I need an x integral because my slices are vertical, so their thickness is a small change in x. And this is supposed to be a formula for the volume of a cylinder. Well, here's the height of the cylinder, the dx. The other part of the volume formula comes from the area. So the area, what does the slice look like? If I looked at that, it would look like a green circle, right? So the area of a circle, pi r squared. Can I strongly suggest you make your parentheses and your square first and then try to fill in the r? It's going to be 6 minus 4 natural log, except give yourself more room than I did. 3 minus x. I am assuming, right, so I would not expect on the AP test that you'd be asked to actually integrate this. I would expect it would say something very specific like write, but do not evaluate an expression for the volume of the solid formed, and that's what we have here.